Hi everyone, in this video we're going to go through section 9.1, estimating a population proportion. And what I say at the top is this is likely the most frequently reported type of confidence interval. So confidence interval is something that we're going to have defined for us a little bit later in the section. But really, it's the statistic that we encounter most often in our daily lives, I think. And our goal here is formally stated to estimate the value of an unknown population proportion. And what that means is use sample data to tell what everyone else is thinking. And we'll write the definition here for a point estimate, and that is a value of a statistic that estimates the value of a parameter. And so a point estimate for the population proportion is the number of individuals in a sample with the specified characteristic over the sample size. And that is the p hat that we saw in the previous section. So just a quick example here, we've got a poll was conducted in which a simple random sample of 1,020 Americans age, what does it say there, 18, there we go, or older, were asked, do you consider the amount of federal income tax you have to pay is too high? 490 said yes. So we've got 1,020, 490, obtain a point estimate, that's the new definition, for the proportion of adults who believe it is too high. So we take our 490, the numbers that said yes, divided by 1,020, and we get, in your calculator, 0.4804, or about 48%. So that's our point estimate. That's the number that we use to make a statement about what the population thinks. This is what our 1,020 people think, but how do we take that and make an inference about the whole population? That's what we get to do in this section. Okay, and here we get a refresher from section 8.2. So this is not new information, but it is something that we saw in the last section. We have the sampling distribution of p hat. How do we create that distribution? Well, if we have a random sample of size n, the distribution is approximately normal with a mean equal to p and a standard deviation equal to, well, we use our formula to compute the standard deviation, and it's normal provided that we have n times p times 1 minus p is greater than 10, greater than or equal to 10. And so we verify normality with the distribution of p hat. And then we have the 5% of the population. Our sample size has to be smaller than that. So this is just content that we saw in the last section that will still apply here. Okay, so a confidence interval. I mentioned it earlier here. What is it? For a confidence interval for an unknown parameter consists of, well, it's an interval of numbers from this to that. It includes a level of confidence, and that represents the expected proportion of individuals that will contain the parameter if a large enough number of different samples is obtained. That's kind of heavy, but we'll investigate what that means in a little bit. Then the level of confidence, the notation for it, a little bit wonky, is denoted 1 minus alpha times 100%. So we'll get a little bit more clarity on what that means a little bit later. Okay, so a 95% level of confidence means that 95% of all possible samples result in confidence intervals that include the parameter, 5% do not. And confidence intervals, what they look like is a point estimate, a number, plus or minus a margin of error. So it's a number plus or minus a margin of error. So the margin of error is a measure of how accurate our point estimate is, and it depends on three things. It depends on the level of confidence, right? If I want to be more confident, that means that I have to give more room for error. However, if I want to be less confident, then I can leave a smaller room for error. And then sample size, think about if you have a really, really big sample size, like almost as big as the population, not likely going to happen, but the sample size, if it's really, really big, it's going to create a really, really small margin of error. And then the standard deviation also affects the margin of error as well. But how do we actually construct a confidence interval? Let's look at that in this next example. So we go back to the 1,020 Americans age 18 or older. 490 of them think that the amount of federal income tax they have to pay is too high. And there is a 95% confidence that the max sampling error is 4 percentage points. Okay, so what that means is we take our p hat that we computed earlier, which was, I'm going to round it to 0.48 for this example, 48%. And to create our confidence interval, we take that 0.48 plus or minus 4%, 0.04, 4 percentage points. And that creates an interval, and we write it in interval notation with parentheses and a comma. You subtract the 4%, you get 0.44. You add the 4%, you get 0.52. And so the statement that we make about our population is we expect between 44 and 52% of the population to think that their income tax is too high. Okay, so that's the inference, the conclusion you make about the population. So when working with confidence intervals, we have common ones that we'll see very often, and there's a table within Table 5 at the bottom. So at the bottom of Table 5, we have these common confidence levels, and then the area that they leave in each table, as well in each tail, as well as the critical value that they correspond to when we get to the formula that we're going to be using. And then how do we interpret a confidence interval? What is the sentence, the formal statement that you write, or that you can write, to interpret a confidence interval? And it's a blank percent, and so it left off the percent there. A blank percent confidence interval indicates that blank percent of all simple random samples of size n from the population whose parameter is unknown will contain the parameter. Okay, so that's the formal statement for what it means. But we'll see through these examples that we'll get to how that works, how that makes sense. Okay, and on this slide, we get the official formula for a confidence interval. And the one on the left and the one on the right are essentially the same thing, and I'll explain the difference. But this is how we construct our confidence interval, and it's p hat, as we saw in the previous example, p hat plus or minus, and it's a z-score times a standard deviation. And that z-score times standard deviation, that part of the formula, represents the margin of error. Okay? And so that's on the left. But on the right, what we've got plugged in, what we've got substituted in for the z-score times the standard deviation is really just the standard deviation formula. So this is the same thing, but with the standard deviation formula plugged in. Right there, that guy is the sigma sub p hat. Okay, so the left and the right are the same. The one on the right is more useful. The one on the left is more condensed, I think. And then when it says at the bottom, notice that p hat is used in our standard deviation formula. Right, when we did it in the last section, we didn't use p hat because in this case we're estimating what the population proportion is. We don't know it ahead of time, so p hat is our best guess, our best point estimate for that population proportion. Then, just to give you a little visual of hopefully why that formula makes sense, first let's take a look at this picture that I took a nice little screenshot out of the book. Right, we have our unknown parameter p. That's this p right there. We don't know what that is, but if I take a sample, that's this p1 hat, and add and subtract, that's the red bar down here, 1.96 times the standard deviation, because I'm creating a 95% confidence interval, right? Does that interval of numbers include the parameter p? Yes, it does. Okay, so the 1.96, that comes from it being a 95% confidence interval, right? And then if I take another sample, p2 hat, there is a chance that 1.96 times the standard deviation does not include the parameter p. But conceptually, it's a 95% chance that it will contain, 5% chance that it won't contain. So really, what would it would look like is if I move down a little bit more. Now, this is a ridiculous looking picture, but what it is it represents lots and lots and lots of confidence intervals. So each of these horizontal bars or horizontal lines is its own confidence interval, and every time, or not almost every time, they contain the parameter. In this case, 0.7 is the parameter p, and every green interval contains that parameter. 95% of the time, my sample proportion, that the confidence interval that it creates, includes the parameter p. But every once in a while, here we get 1, here we get 1, here we get 1. Every once in a while, the interval does not include the parameter, and there's only a 5% chance of that happening. So very rare, still possible though. So that's what this is kind of a visual of what the 95% confidence interval means. And if I scroll back up here, this is kind of maybe why the formula should make sense. 1.96 is 95%, it creates the 95% confidence interval that moves us out from our center point, the p hat. Okay, so now we get to our first example where we're actually going to construct a confidence interval. And in this example, we have 800 individuals, age 16 to 17, and they were asked if they text while they drive. 272 indicated that they do. 272 out of 800 said, yes, I text while I drive. The other ones were all lying. But we're going to create a confidence interval, 95% confidence interval, for the proportion of 16 to 17-year-olds that text while driving. The first step to doing that is to get our point estimate p hat, which in this case, 272 said yes, 800 in our sample, 272 out of 800, check it in your calculator, that is 34%, 0.34. That's our starting point, our point estimate. So then from there, we go p hat, we create our confidence interval, it's p hat plus or minus our z-score times the standard deviation, which is p hat times 1 minus p hat over n. So p hat is in 3 different places. We already know what that is. So I'm going to plug that in those 3 places, 0.34 plus or minus under the radical 0.34, 1 minus 0.34. I can also plug in my n. My sample size is 800. The only additional piece of information I need here is this z-score. And the place that comes from is the 95% confidence level, confidence interval. So that number tells us to go to table 5, and if it's one of the common ones, we can luckily look at the bottom and see what that corresponds to. And in this case, a 95% confidence level corresponds to a z-score of 1.96. 1.96 there. Okay. If it was 90%, we'd use that from the bottom of table 5. If it was 99%, we'd look that one up. If it's some more obscure percent, I'll have an example in a little bit where we find that. Okay. So now when I type this into my calculator, what I do is I take my 0.34 plus or minus, so we'll leave that as is for right now, and I'm going to type in the 1.96 times the square root of 0.34 times 1 minus 0.34, but I typically do that subtraction ahead of time, and you get 0.66, and then divided by 800, and all of that leaves you with 0.033, if I round to 3 decimal places. If I only round to 2, just 0.03. So make sure if you do not do the 1 minus 0.34 ahead of time that it gets its own parentheses. Otherwise, it's pretty straightforward. You don't have to do anything exceptional when you type this into your calculator. I just like to do that subtraction ahead of time. All right, so then we add and we subtract to create the interval of numbers. 0.34 minus 0.033 is decimal point 307. And then when you add 0.033, you get decimal point 373. Okay, so what that means is that between, and I'm not going to write this out, but I will with a later example, between 30.7 or 31% and 37.3 or 37% of the population of 16 to 17-year-olds text while driving. We're 95% confident that the population, the parameter, is between those two numbers. There's a 5% chance that it's lower or higher, but a 95% chance that that's what is representative of all the 16 to 17-year-olds. In our next example, we go back to politics in 2016, and we have a real poll out of New Hampshire where we have 107 voters indicating Donald Trump as their first choice for Republican nominee for president out of a sample of 410 individuals. And we need to obtain, I'm going to change that 95% confidence interval just to give you an example of one where we have to find it on our own. We're going to obtain a 92% confidence interval for the proportion of individuals that prefer Donald Trump for Republican nominee as president out of all the voters in New York State. So we're taking a sample and using it to draw a conclusion, make an inference about a whole population. Okay, so our formula for confidence interval, p hat plus or minus our z-score, alpha over 2, times the square root of p hat times 1 minus p hat over n. Okay, so the first thing that we'll find, all right, we already know what our n is in the formula. That's the sample size, 410. We can compute p hat without too much difficulty. I'll put it up here. P hat, our sample proportion, 107 out of 410, and plug that into your calculator, and you get about 26%, 0.261 if you round, but I'm going to go to the nearest tenth, or to the nearest hundredth, 0.26. So that's the first piece, and that goes in 1, 2, 3 different locations in our z-score, or in our confidence interval formula. Okay, the only other piece that we have to find is the z-score, and I gave you a more obscure confidence interval in this one, and I'll show you how to find that z-score using table 5. So let me draw my distribution here. There we go. Okay, the middle is the mean, the p hat, the z alpha over 2. So what that means in our distribution, okay, is if I have a 92% confidence interval, 92% of the stuff is between, 92% of the area is between those two values. All right, so this z alpha over 2 over there, this z alpha over 2 over there, this one would be negative, the other one would be positive. Well, how do I get that z-score? If 92% is between those two values, well, what would be on the outskirts? Well, 8% is left over out of 100, so that would be 4% over here and 4% over there. So to find those two z-scores, but really all I need to do is find one of them, I'm going to go down to table 5 and find 4%. And I think I need to zoom in a little bit more. So from within table 5, I'm going to go ahead and I need to find 4%. So I start out in the middle, go down until I get close to 4%. There's 2%. 3%, there's pretty close to 4%, 0.0409. Move to the right, 0.0401, that's really, really close to 4%. So there's our number there. Ooh, where'd it go? There it is, 0.0401. And then what z-score corresponds to it? Go out to the left here, and you have negative 1.7. Go up, and you have 5. Negative 1.75 is our z alpha over 2. Negative 1.75. And then if you go down to, instead of looking up 4%, if you look up, let's see, what would it be? 96%, and I'll show you why I just said that number. If you go down to 96%, 96% is somewhere down here, 9671. Let's see, where are we really close to 96%? Let's see, where is it? Oh, there we go. That's really close to 96% right there, 9599. And that's positive 1.7. You can't see the top of the table, but it should be the same z-score, positive 1.75, and it is. And that's why in the formula there is a plus or minus, one representing the left-hand side of our z-table and one representing the right-hand side of our z-table. So going back up to my problem, that z-score, we can zoom back out now, I think. That z-score that we need, z alpha over 2, is plus or minus 1.75. So if you're lucky and it's one of the common confidence intervals, just look it up at the bottom of the table. If you get a more obscure one, that's how you find it from within the table. And then the reason that I went at the bottom to 96% is because on the right-hand side, take 4 from 100, that's 96%. All right, so substituting everything into our formula, 0.26 plus or minus the z-score, 1.75 times the square root, 0.26, 1 minus 0.26, divided by, what was our sample size? 410. I'm typing in just the plus or minus part into my calculator first, and we get plus or minus, let's see, 0.038, 0.038, or about 4%. So then we take our 26% to actually create the interval. 26% minus 4% is 22%, 0.22, add 4%, and you get 0.30. And that is our interval for what we expect all of the voters in New Hampshire to do. Between 22% and 30% of all the voters in New Hampshire would vote for him as their Republican nominee. And we're 92% confident that the interval contains that parameter. This next example, I'm not going to do all of it for you. You can choose to do it on your own if you want to. What I'm including it for is because it has the formal statement at the bottom of the problem. So my conclusion here, and you would just fill in the blanks if you want. If you do the problem, we are blank % confident. That comes from the confidence interval right over there. We are blank % confident that the proportion of teenagers between 12 and 17 who contribute to content on the internet is between blank and blank, and those would be the endpoints of your interval. And so that's like the formal statement. If you can write some sentence that makes sense like that, then you're golden. In this next slide, we get a little bit more detail, I guess, about the margin of error. So in the confidence interval formula, we have the plus or minus part, the part that you add and subtract to your p hat. And it's the z sub alpha over 2 times p hat 1 minus p hat over n, all under the radical. And that is called the margin of error. So we can compute it, we can talk about it as its own thing. How does each of these pieces, and I've kind of alluded to this already, affect the margin of error? A really big sample size will help to minimize the margin of error. A really weak level of confidence can also help to minimize the margin of error. And so these are all things that you can play around with, and I'm not going to do any examples of them, but if you increase not from your confidence level in one of the earlier examples from 95 to 99%, how much does that affect the margin of error? It should make it wider. If I want to be more confident that my interval contains the parameter, contains what the whole population thinks, right, then it needs to be a little bit bigger. The interval needs to be bigger. And then how does sample size affect the margin of error? If I increase from 800 to 8,000 in the previous example, how significantly does that affect the margin of error? And that's all stuff that you can play around with using Minitab, but I'm not going to go into specific examples. But if you increase it from 800 to 8,000, the interval should get smaller, but by how much? That's where it gets a little interesting. One thing we can do with margin of error is solve for or determine a sample size necessary to have a specific margin of error. So let's say I end up, after I do all my research and get a margin of error of 4%, I don't want to report results with 4% margin of error. So how big of a sample size do I need to make that margin of error a little bit smaller? And that's something that you can do if you do the work ahead of time. And we do that by solving the error equation for n. And so let me rewrite my error equation. Z alpha over 2 times the square root p hat 1 minus p hat divided by n. So we'll go through the algebra steps. Our text does give this as its own formula, but just to see where it comes from, if I want to solve for that n in the denominator, that guy right there, whoops, wanted to highlight it. There we go, that guy right there. And rather than go through all of the steps of solving for n, I'm going to take and just write down what you end up with. N is equal to p hat times 1 minus p hat times z alpha over 2. That's a terrible alpha. Let's try that again. Z alpha over 2 over e squared. So I just put that in there as its own formula. Those of you that love algebra, feel free to see if you can produce that from the original error equation. But that's the formula that we use. And then sometimes if I don't have a good prior estimate for p hat, if that's not available, if I haven't done my research yet, or my math lab doesn't give me that number, we can substitute a 0.25 in for those two parentheses. That only happens when you don't have a p hat to work with. Then for the question at the bottom, we'll go back to the texting and driving example where our p hat we found to be 34%, 0.34, and we want to know how big our sample size has to be to estimate the proportion with a 2% margin of error and 95% confidence. If you remember, the margin of error in that one was a little over 3%, I think. But now what if I wanted to report better results? I want to have a smaller margin of error. Well, I can substitute into that error formula. Oops, not E equals, it's N equals p hat 0.34 times 1 minus p hat times the z-score was 1.96 for a 95% confidence interval over E, the error in this one, I want a margin of error of 2%, 0.02, and then that parentheses is squared. And I'm not sure why I wrote p hat there, but it should be 0.34. Then if you type all that into your calculator, you get 2155.1376. Okay? And we're going to round that to 2,156. Even though that's a 0.1 there, in this instance we would round up. We need that next person in our sample to have our 2% margin of error. So even though it's 0.1, we automatically round that up. And pay attention to the blue words in my math lab for rounding on these problems. But we find that we need 2,156 people instead of the original 800 to minimize that margin of error to only 2%. So you need more than double the people to get that smaller margin of error. But if you rerun the test and get the same results, you now can report that, our margin of error is only 2%. We have a much smaller confidence interval, much more condensed packed interval that contains what the population of individuals think. All right, so this was a little bit lengthy of a section. It likely would have taken me 2 days in class to get through. Thank you for listening and suffering through all of this. Hopefully it wasn't too terrible. Get to work on the homework. Let me know if you have questions. And again, thank you for listening.